make a very quick announcement. So the Nerode Prize is sponsored by IPC and EATCS. And it's a prize for work in anything to do with kind of multidimensional analysis of algorithm, meaning like there's more than one size parameter or parameter that impacts time. Or anything where we're looking at complexity at a finer algorithmic complexity at a finer grained level than usual. So pretty much anything that you would be interested in that brings you to this workshop would kind of qualify for the Nerode Prize. We're a little bit behind schedule in announcing the prize, so I really would love more nominations. I think that means I'd love a positive number of nominations. The deadline is next week, May 31st. So all you have to do to nominate someone is to send these people email with the subject Nerode Prize nomination, and then describe the paper that you want to nominate. Paper or set of papers that you think should be nominated. And yes, you have to, so you're supposed to send it to all three of these email addresses, but if you send it to me, I'll guarantee that I'll forward it to the others. And I also have, if you can't remember my whole last name, russell@cs.ucsd.edu works as well. Okay, thank you.
So the next speaker will be Mirza, but talk about K-dominating.
Thank you for the introduction. So yes, I'll be talking about K-dominating sets, and in particular, how does sparsity contribute to, or how does it affect the complexity of detecting a K-dominating set? This is a joint work with Nick and Marvin, and I don't think any of the two are here today. But yeah, this is from Soda last year, so if you want to find, like, the paper is also under this title. All right, so let's dive into it. So let's suppose you have a social network and you want to spread a piece of information among, like, all of the people ideally. And since, like, we are computer scientists, we don't want to talk to a lot of people ourselves, so we would much rather hire people to do it for us. So we want to hire so-called influencers to spread this piece of information throughout the network, so that, like, the whole network gets this information, right? So in this particular example, if k is equal to 2, we can just take these two nodes, and, like, it's not hard to see that everything is somehow connected to either one of these two nodes. So formally, this is a well-known K-dominating set problem, where you're just given a graph G and want to find out if there are k vertices x1 up to xk, such that their closed neighborhoods, basically, the union of their closed neighborhoods contain the full vertex sets. Okay. I guess you all knew about this problem, but just to refresh your memory. So I won't try to convince you that K-dominating set is a fundamental problem. You'll probably know this, but just to recall, it's a classical NP-complete problem. It's the most natural W2 complete problem, and it's among the first problems for which typed strong ETH-based lower bound has been given in 2010 by Petrashko and Williams. All right, so this lower bound is n to the k, and Eisenbrand and Grandoni gave an n to the k upper bound, so we have a matching upper and lower bound. So yeah, a natural question that you might be asking is, what are we doing then? Well, this lower bound in particular generates dense graphs. So it doesn't answer the question, what about what happens if the input graph is sparse? Can we get better algorithm in sparse graphs? Like, in particular, could we halve this exponent? So can we get an m to the k half if the graph is sparse? And it's not hard to see that this cannot be done. Like, a simple modification of this particular lower bound gives like KOV based lower bound of m times n to the k minus 2. So we can pretty much in very sparse graphs, so if m is equal to n, only shave off one factor of n, right? I won't show you this lower bound, but I'm pretty sure that everyone can work it out on their own, like it's quite simple. But I will show you the upper bound. So let's recall the classic like Eisenberg-Mendoni algorithm from like, I don't know, 20 years already. Okay, so if we're given a graph G, let S be any subset of vertices, right? So we will define this vector Vs, where intuitively each entry will correspond to a vertex in our set V, and we will have a 0 in position I if the set S dominates E, dominating like S dominates E if there is either a vertex in S that is adjacent to sorry, not EI, or if I is in this set. All right. Now let's look at the product of like the inner product of two such vectors. So now we have two sets S and T, and if we look at their like vectors, Vs and Vt and their product. So what happens if we have like one at position J in both of these? What does this mean? Well, this means that like S does not dominate J, nor does T dominate J. In particular, this means that their union does not dominate J, right? But this in particular means that like this inner product precisely counts the number of vertices not dominated by the union of S and T, right? So I guess you already see where I'm going with this. So now we just come up with, like, we just need to design matrices somehow, so that every dominating set can be written as kind of the union of like the guys that correspond to rows in one matrix and columns in the other. And like in general, like in the classical algorithm by Eisenberg and Grandoni, they basically just take S and T to be equal and just set them to, so each row basically will correspond to, or each set S would correspond to a set of K half many nodes in the graph and T as well, and then like just construct the matrices. And we will do something similar, but we will, on top of that, use the following observation. So the average degree of a vertex in any K dominating set is n divided by K, right? So in particular, what this means is that any K dominating set contains a vertex of degree at least this, and we will call this vertex heavy. And now for a constant K, we have m edges and the vertex of this degree, and like it's easy to see that there are at most O of m divided by n such vertices, right? Okay. So just to free up some space, I'm summarizing that here. Okay, so now let's define these calligraphy S and calligraphy T sets. So okay, this notation is maybe a bit confusing, but basically this calligraphy S will be set of all subsets of V of size K half essentially that contain a heavy vertex. And T will just be set of all subsets of essentially K half lines, right? And now if we define matrices B and C as follows, so each row of matrix B will be indexed by an element like a subset in S, and each column of C will be indexed by subsets in T, and the rows will correspond to VS and columns here will correspond to VT. Then we get what we want. Basically, if we just multiply these two matrices, what do we need to check in the product matrix? Well, we just need to check if there is a 0, right? Because each entry will correspond to such an inner product. And if there is a 0 in product matrix, then like the precise entry will correspond to a dominating set. And we'll be, okay? So how fast can we do this? Okay, I hope the color choice was fine. So size of S will be this thing here up to a constant, right? So m divided by n times n to the k half minus 1. Why is this? Well, it's essentially n to the k half, but one vertex has to be heavy. So as we said, like we replace one factor of n by n divided by n. and clearly like size of T will be just n to the k half. Okay? So how fast can we multiply these matrices? If k is at least 9, this is precisely m times n to the k minus 2 by using the rectangular matrix multiplication, let's say, for the art. I think this was also the question that came up yesterday during some talk. And this precisely matches our lower bound, right? So in this case, we are pretty happy. I don't know if you can see, but this is a happy watermelon here. Okay? If k is strictly smaller than 9, what happens then? Well, unfortunately, with the current rectangular matrix multiplication, we cannot really match this, but we are left with some polynomial overhead. And in this case, we are somewhat sad, and this is a sad watermelon. But we can still ask a question, okay, maybe we don't resolve this with current matrix multiplication, but what if omega is equal to 2? This is a fair question, right? Can we resolve this up to resolving the matrix multiplication, right? And well, I claim that, well, first, this is a confused watermelon, but I claim that there is still one case that we cannot resolve. I guess this is a bad news because like we still need to like construct an algorithm for one more case. Does anybody see which case we are missing? All right, so I will just tell you. Like the case we are missing is k equals to 2, and we'll figure out why. But good news is, if there wasn't such a case, this would be a pretty boring paper. So at least like we got that for us. So what happens if k is equal to 2? Let's just plug in the values here for k half and k half. So like k half will be 1, so like this will be just the set of heavy vertices, right? So this term vanishes, so we only have m divided by n here. All right, and this will just be set of all vertices, right? They're just plugging in k. So this will be m divided by n, this will just be n, and these are the dimensions of our matrices, okay? What happens now? If we look at this guy, we run into a first problem. This guy can contain up to n squared many ones. And now just reading the input requires time n squared. But for k equals 2, we don't get any non-trivial lower bound. So this m times n to the k minus 2 is precisely linear if k is equal to 2, right? So we don't get any non-trivial lower bound. So we are still off. Okay, so if you recall the construction of C, it was basically like the columns for these vectors VT, but each of these vectors was basically a complement of the adjacency vector, right? So we had a 0 if it doesn't dominate and 1 if it dominates. So up to like the diagonals, it was just complement of the adjacency vectors. So what if we just complement this? Oh yeah, I even wrote that. So what if we just complement this matrix? We basically get adjacency matrix, and now we no longer have this problem, right? But now we lose this property that we just have to look for a 0 in the product matrix, okay? So let's see how to fix this. All right, so the question that we want to answer now is, by looking at the product of these two matrices only, can we tell if there exists a dominating set? All right, so let's start by considering one dominating set ST of side 2. And let's look at the row of B corresponding to S and the column of C bar corresponding to T, like the complement matrix. All right, if there is a V, vertex V in our graph, such that this entry is 1, what do we know about like this entry here? ST is a dominating set. This one tells us that S does not dominate V, right? So what we must have is that T must dominate V because ST is a dominating set. So we must also have 1 here because this is a complement, right? But then in particular, what do we get from this? Okay, yeah. So if ST is a dominating set of G, then in the corresponding entry, ST in the product matrix is precisely equal to the number of non-zeros in the corresponding row of S in B. Okay, does this make sense? Any questions at this point? Cool. But it turns out that we can also prove the other direction of this equivalence, and these two conditions are equivalent. So we can tell if something is a dominating set by just looking at the product matrix of like B and C bar, and like if the corresponding entry ST has this is equal to the number of ones in the row S, then this is a dominating set. Otherwise, it's not. Okay. But now, okay, yeah. So let's write this down more succinctly. So basically, in terms of vectors, this is to say that the inner product of Vs and Vt bar is equal to the weight of Vs if and only for the dominating set. So now we run into another problem. So basically, the number of columns of B is equal to n, and the number of rows of C bar is equal to n as well. So then to multiply these two matrices, even if omega is equal to 2, we need at least n squared time, right? But the good news is that we don't really need to multiply these two matrices. We just, like, we don't care about the total product. We just care if there exists one such entry in the product matrix. And so, yeah, so the problem is that the inner dimension is still too large, and we solve this by hashing, of course. Okay, so now, how do we hash? Okay, so yeah, let's make first an intermediate assumption. This is just for simplicity, and we will work around it a bit later, that the matrix C bar is fairly regular, which means that each column will just have between R and 2R many non-zeros, essentially. But this implies, just by like simple counting argument, that C bar has at most M divided by R many columns, right? We will use this to analyze the time complexity later. Okay. So let's take a uniformly random hash function H that will basically contract the universe of size n to the universe of size 4R. And we will construct matrix B prime by hashing the columns of B in a following sense. So we take an entry SY to be just the or of all the guys, of all x's that hash by H to Y, and we just take like the or. Essentially, just if we have one in the whole bucket, we make the whole bucket equal to 1. That makes sense. All right. And then we just do the same thing for C, but just the rows instead of columns. Okay. So now it's pretty easy to see that we don't get any false negatives. So if ST is a dominating set, then in the product matrix, we will have this thing satisfied. And why is this? Well, let's assume that we do get that this does not hold for contradiction. So then this only does not hold if there exists a Y such that in the corresponding vector such that like the corresponding entry here is 1 and in the other place is 0. But let's unwrap this. What does this mean? This means essentially that there exists some X that hashes to Y by this hash function, and the corresponding value in B is equal to 1. This is the only way that we get this one, right? But ST is a dominating set, which means that also C bar XT will be 1 by the condition from 2 slides before, right? But then this guy cannot be 0, and then we get a contradiction because like this is the same X, and it will also hash to Y. Right? Make sense? Any questions here? Okay. All right, so mouse moved. Okay. But also, we have in the other direction the following claim, which I will not prove, but it's also not too hard to prove. If we don't get a dominating set, then this thing is satisfied only with constant probability. So false positive probability is at most 1/2. All right? But this is now cool because now we can just boost this probability by repeating the algorithm like 100 log n times with just newly sampled hash function every time. And we get like n to the minus 100 error probability roughly. Okay. All right. Now I will just tell you about the time complexity. Why do we get I claim that we get near linear time algorithm with this hashing approach, if omega is equal to 2, of course. And I will prove this claim here. We can prove a better, not better, but we can prove for any omega some cool bound, but I won't bother with that because it would be a bit of an overkill for the talk. So basically what I will use is that you can multiply matrices if omega is equal to 2 in time that equals to maximum of the pairwise products of the dimensions, okay? So this is what I'm using. All right. This thing is, if you recall from a few slides back where we used this intermediate assumption that each column of C has between R and 2R many ones only, right? So we can only have this many columns, right? And this is a trivial bound. All right. So I'm just here, I'm not doing anything fancy. I'm just multiplying each pair of dimensions. And now I'm just plugging in the minimums here, the minimas. So here I'm plugging in n to cancel these two guys. Here I'm keeping this the same as this. And here I'm plugging in this guy and I will cancel r's. Okay, so this is how I get this. All right, now after canceling, we get this. Okay, so this is, we're happy with this, we're happy with this. But look, if we look at this guy, are we also happy with this? Well, we should be, because if we recall what R was, we basically hashed the n size universe to R size universe, right? So if this is larger than n, it doesn't really make sense. Okay, so this is at most n. And then by using that, this is at most n, we can just plug in n here and cancel out n, and this will be just linear time. Okay, fair enough. Right. So basically, we assume this fair regularity that each column has between R and 2R many ones, but we can basically split the matrix column-wise into matrices like C1 up to C log n, where each CL has between 2 to the L and 2 to the L plus 1 many non-zeros, and then just do this you only need to repeat this algorithm log many times. So this is also, I guess, we can hide this in subpolynomial vectors. Okay, yeah. All right. The second part of the talk, so this was all about dominating sets. I don't know, I have 5 minutes, so I guess I won't go into the details here, but I will just try to just give you the results that we obtained here in hardness of monochromatic basic problems. Okay, so the natural question now to ask is, for which related problems to dominating set does sparsity affect the complexity? We can observe that K-dominating set, to study this somehow systematically, what does it mean, related? We just noticed that K-dominating set is a first-order property of the following form, so we can write it as exists x1 in V up to, V1 in V up to Vk in V, such that for every W we have an edge to at least one of these guys, all right? And so Gao and others solved this, show that you can solve every such FOP in m to the k time, okay? But also there's a list of so-called basic problems of form exists V1 in V1 up to Vk in Vk, such that for all W in W we have this this formula with literals L1 up to Lk, where each Li is either edge, so E of Vi and W, or non-edge between Vi and W. And intuitively, these are the hardest FOP problems. You can reduce if you can solve this, if you can beat this running time for these problems, or one of these problems, you can beat it for every problem, essentially. Okay, we also observed that K-dominating set is a canonical monochromatic variant of KOV, which is one of the basic problems that we saw. In what sense do we mean this? Well, if we write these formulas like next to each other, you can see that they're very, very similar. Basically, just by replacing V1 up to Vk by V and here W by V, everything else is the same, right? So this is why it's monochromatic, and we call these multichromatic problems, right? And so now a natural question that arises is, since for KOV in sparse graphs, we cannot do anything, for K-dominating set, we can. The natural question to ask is, are monochromatic basic properties always easier in sparse graphs? Okay, and the answer is no, but we will get to that. Well, I guess I have 3 minutes. So to do this, we consider 3 classes of problems. Multichromatic, which is like KOV, where you have like each quantified variable coming from a different set. Then bichromatic, where you have bichromatic basic problems where you have existentially quantified variables coming from one set and universally quantified from a different set. So an canonical example is K-set cover. And you have monochromatic, like K-dominating set, where you can think of these as graph problems. So you can think of these as vector problems, these are set problems, and these are graph problems, like intuitively, right? Okay. And now we know that these are hard. We know that there's at least one easier problem, namely K-dominating set. But we want to show that for all other problems, we can reduce this guy to this guy. And to do that, we will go over these bichromatic ones. So unfortunately, I'm running out of time to show you the reduction, but basically, like, the idea is to start from K-orthogonal vectors and show that, like, I mean, this is already known, but just for completeness, it's very simple also reduction. Every multichromatic basic problem can be reduced like from orthogonal vectors. And then this reduction, basically like both this one and this one are simple in the randomized sense, but we also provided like the randomization of these. And the randomization here uses some combinatorial gadgetry, and here we use polynomial methods to de-randomize. But yeah, you can easily construct the randomized reductions here. And the important note is that all of these reductions preserve sparsity. So we know that K-orthogonal vectors are hard in sparse graphs. So then every monochromatic basic problem, except dominating set, for which we cannot reduce directly, is also hard in sparse graphs. So we cannot solve them better than n to the k, even if like we have linear number of edges. All right, thanks for your attention. This is all.
Questions for Mirza?
Yeah.
Are there any arrows back, whether you show equivalence or?
This is a great question, but I don't know. We did not consider the other direction, but shouldn't it be easy?
Yeah,
It should be trivial. I don't know.
yeah,
I think it should be easy, right?
you see like randomly partition the.
Yeah, pretty much like some color coding or something. It should work
Yeah.
out. Yeah. Yeah, but good question. I did not think about this. We like focused on the graph type problem. So all of these problems can be expressed in terms of like neighborhood containment type queries. So then this was also pretty cool, like that they appear also naturally as these types of graph problems. So we did not consider the other direction, but it feels like it should be just some color coding argument, and then it should work out. Yes.
The techniques you showed for 2 dominating set, could they help with like 3 dominating set if you don't assume omega's 2?
I don't see why not immediately. And yeah, so in the follow-up work, we also considered some other domination type problems where you also want your dominating set to adhere to a certain pattern. So for example, you want your dominating set to be a clique in your graph. And in this case, for 4 cliques, for example, we applied the same techniques and they actually worked out. But it needs a lot more work in terms of how you partition your vertex set, and you have some case distinctions with like analyzing time complexity. Basically, this is the harder part. Like if omega is equal to 2, then it works out directly. But showing precise like running time that you can like bounding this in current matrix multiplication requires some additional work.
More questions? Yes, thank you, speaker.